All right, welcome to this explainer, where we're going to dive into a chemical reaction that seems to have a mind of its own. Seriously, it's one we can command to go forwards, then backwards, and even change color just like that. But what you're about to see isn't magic, not at all. It's the science of equilibrium, a principle that is constantly at work everywhere around us.
Okay, so let's kick things off with what honestly looks like a magic trick. We've got a chemical reaction here, but it doesn't just go in one direction. You see us mix two totally clear liquids, and boom, they react to form something new. But that, believe it or not, is only half the story.
Because, and this is the wild part, this reaction can actually run in reverse. That new stuff we just made, it can break back down into the exact things we started with. It creates this constant push and pull, this dynamic dance that, as we're about to see, we can actually learn to control.
So here's the actual experiment. We mix two clear solutions. One has iron ions, the other has thiocyanate ions, and instantly, the whole thing turns this deep, blood red color. Now, watch this. If we add a little more of one of the starting ingredients, the color gets even darker, even more intense. But then, if we add something totally different, like silver nitrate, the red just vanishes. It fades away completely, leaving this white solid behind. We can literally make this color appear, get darker, or disappear right on command.
So what on earth is going on here, right? How can a reaction be pushed and pulled back and forth just like a seesaw? Well, the answer lies in this beautiful concept called chemical equilibrium.
To really solve the mystery of our color-changing liquid, we first have to get a handle on the principle that's working behind the scenes. It's this constant, invisible balancing act that's happening at the molecular level.
And that state is called dynamic equilibrium. The key word here, you guessed it, is dynamic. The reaction has not stopped, not even close. It just means that the forward reaction, the ingredients turning into the product, is happening at the exact same speed as the reverse reaction, where the product breaks back down into the ingredients. And this quote just illustrates the idea perfectly. Imagine one person furiously shoveling dirt out of a hole, while someone else is shoveling it right back in at the exact same rate. Now, even with all that activity, all that work, the size of the hole doesn't change, does it? That's dynamic equilibrium. To our eyes, that red color in our beaker looks totally stable, but down at the molecular level, it's organized chaos, a constant balanced dance of molecules forming and breaking apart. So if it's a balancing act, how do chemists keep score? How do they know if the seesaw is tilted more towards making the product or if it's tilted back towards the starting stuff? They need a way to put a number on it. And they do that with a value called the equilibrium constant, or Kc for short. At its core, it's a pretty simple ratio. It's the amount of products you have divided by the amount of reactants you have, once everything's settled down into equilibrium. So if Kc is a really big number, way bigger than 1, it means you've got way more products than reactants. We say the equilibrium lies to the right. If Kc is a tiny little number, way smaller than 1, it means you're left with mostly reactants. The equilibrium lies to the left. And if it's somewhere around 1, you've got a pretty healthy mix of both.
Okay, so every reaction has its natural balance point. But what if we want to mess with it? This brings us to the tool that lets chemists become the master controllers of a reaction. This is how we get to tip the scales.
And it's all explained by something called Le Chatelier's principle. It basically says that if you stress a system that's at equilibrium, by changing concentration, temperature, or pressure, the system will shift to try and counteract that stress. It fights back. So, back in our experiment, when we add more iron ions, that was a stress, and the system responded by shifting to the right, making more of that red product to try and use up some of that extra iron we just dumped in. It's always trying to find its balance again.
Now, here's a really crucial point. When you change the concentration of something, you're just shifting the position on the seesaw to get back to the original balance point. The Kc value, that fundamental ratio, it doesn't change. But when you change the temperature, you are fundamentally changing the balance point itself. The value of Kc actually changes. You're not just rebalancing the seesaw, you're redesigning the whole thing. It's a really important difference.
So, this all brings us back to what we can actually see. How do scientists turn a simple observation, like, hey, the color changed, into the precise, hard data they need to calculate something like Kc? Well, the answer lies in something called the Beer-Lambert law. Now, it sounds a little fancy, but the idea behind it is incredibly simple. The more concentrated a colored substance is, the more light it's going to absorb. And that relationship is direct and linear. So if you double the concentration,
You double the amount of light that gets soaked up. Simple as that.
This is all measured with an instrument called a spectrophotometer, and you can see how it works. It shines a beam of light through our sample, but crucially, it picks a very specific wavelength of light, the exact one that our red product absorbs the most. Then, a detector on the other side measures exactly how much light managed to get through. So, by precisely measuring the intensity of that red color, scientists can calculate the exact concentration of our product, and from there, the equilibrium constant itself. Pretty clever.
Look, this isn't just some neat trick you do in a lab. Understanding and, more importantly, manipulating equilibrium is absolutely vital for modern industry. It's how we feed the world.
Let's talk about the famous Haber-Bosch process. This is the industrial process that makes ammonia for fertilizer, and it helps feed billions of people. It operates at these insane pressures, between 150 and 250 atmospheres, and that is a perfect real-world application of Chatellier's principle. That intense pressure is a stress that forces the equilibrium to shift hard towards the product side, maximizing how much ammonia they can make.
But hold on, here's a puzzle for you. According to that same principle, because this reaction gives off heat, a low temperature should actually give an even better yield. So why in the world do these industrial plants run the process at a blistering 400 to 450 degrees Celsius?
And the answer is a classic trade-off. It's a pragmatic compromise. See, a low temperature gives you a fantastic yield, in theory, but the reaction is so painfully slow it would take forever to be useful. A high temperature makes the reaction go way faster, but you get a worse yield. So, industrial chemists picked a sweet spot in the middle, a temperature that's high enough to get a good rate, and a pressure that's high enough to still get a decent yield. It's a perfect balancing act between getting a good result and getting it quickly enough to matter.
And that brings us to one final provocative thought. Our entire analysis of this experiment relies on scientific models, and every model has its limits. That Beer-Lambert law we talked about, it starts to break down at really high concentrations. It's a good reminder that our scientific laws, as powerful as they are still just that, models. They're incredible but imperfect tools that we use to get a handle on a deeply complex reality. Which kind of leaves us with a bigger question, doesn't it? If even our most powerful tools for understanding the world have built-in flaws, how do we ever know it's really true?